Welcome back, everyone. This is the last phase of my project on NYC 311 calls. Now that we've covered the exploratory data analysis and implementation and model testing, I will evaluate and interpret the model's performance. Let's begin by recapping our initial SAR-IMA model findings. Because the NYC 311 call data is time series, I chose to implement an ARIMA model forecasting algorithm. ARIMA is based on the idea that the information in the past values of the time series can alone be used to predict the future values. When I implemented first-level differencing, I achieved a p-value of 0, and the autocorrelation graph remained relatively within the boundaries. However, I saw that every 7 lags went outside of the boundary, which shows us a weekly seasonality in the data. So I implemented an SAR-IMA, which stands for Seasonal ARIMA model, to take care of that. So how did the SAR-IMA model do with forecasting? To evaluate this, I calculated the root mean square error, RMSE, and the R squared of these two lines. These are good indicators of model performance because they represent the goodness of fit of a regression model. I found that this model achieves an R square of 0.71, which is fairly high, especially for a forecast. The ideal value for an R squared is 1, so the closer the value is to 1, the better the model is fitted. On the right side of this graph, the red line highlighted by the gray bar is a 14-day forecast with no actual data. Let's revisit those findings in the context of my overall research question for this project. Can we train a model to accurately predict the response time for certain complaint types? When we are evaluating how the ARIMA forecast model performed, it's important to remember that this R-squared score is from a model that is trained on itself, so it makes sense that the score would be high. Remember, ARIMA at its core is based on the idea that the information in the past can alone be used to predict future values. Implementing SAR-IMA also ensures that the R-squared is stationary versus an ordinary R-squared where there are trends or seasonal patterns. A high R-squared score could be driven by overfitting. In addition, the residual errors mostly fluctuated around a mean of 0, but there were several spikes. These spikes are due to unpredictable and stochastic events that influenced call volume, which in turn we would expect to influence response time. Examples of these events I found included extreme weather events, pandemic, utility outages, and protests. The unpredictable nature of these large events makes it difficult to accurately predict response times. To further evaluate how my SAR-IMA model performed, I wanted to compare it to a random forest classifier, which is a supervised machine learning algorithm. This decision tree-based algorithm can be used for both classification and regression tasks. The X values I chose for this analysis were agency, complaint type, and burrow, which were used to predict a Y value of response time in hours. How did our random forest model compare? The random forest model generated an R-square score of 0.13. With an ideal R-squared score of 1, random forest didn't do nearly as well as SAR-IMA. While this is a bit of a disappointing score, not many other models exist that would provide adequate runtime with a large volume of data included. To conclude, my SAR-IMA model had the best performance with an R-squared score of 0.71. I found random forest to be not effective with our R-squared of 0.13. I also found that this data does not lend itself to modeling due to the nature of 311 calls. The data is unpredictable and stochastic events influence call volume, which in turn can impact response time. Like I mentioned earlier, examples of this were weather events, pandemic, utility outages, and protests, just to name a few. I also found the features I selected did not appear to have much predictive value, even though many complaint types were handled exclusively by 1 or 2 departments. To further the research done in my project, additional data sets could be integrated to model potential stochastic events and how these impact call volumes. One data set I think could be useful is weather pattern data, which could assist in tagging calls in response to extreme weather. Thank you for taking time to listen to my DATA606 capstone project. My email is provided for any further comments or questions.